Yeah. Rodrigo gave us a seminar about the quantum
Nice.
walk.
Nice, great. And I should say I was particularly curious about you guys' interest on quantum walks, and quite happy to be here now. And also quite happy that you are interested in this paper, because I'm particularly fond of it. It's one of my recent works, and certainly one of the works that I quite like. So this is basically about irrational quantum walks, and the title sort of hides a little bit the main topic of the paper, which is pretty good state transfer. All right. Let me first present the setting of this, of what we are studying here. So we start with the graph G, and the understanding is that each one of the vertices is a qubit, and the edges, they represent interaction or energy between the qubits. All right. And basically, we are interested in studying and understanding what happens when you sort of one of your qubits is in one particular state and the others are in an orthogonal state. And then you simply leave the system to evolve in a closed fashion. And this is what we understand by a quantum walk, right? So after time passes, you should observe that each one of these qubits, the states are changing. And this is a sort of like, this is a dynamic phenomenon, all right? Now, what is the physical formalization of this? So the understanding is that we have a Hamiltonian, and the main Hamiltonian that this work is concerned about is this one. So this basically says that for each edge of the graph, okay, I will be summing this particular term, and this term is, so this is the polymatrix X acting on the qubit located at position I. This is the polymatrix, the polymatrix X acting on the qubit in position J, and the polymatrix is Y. Okay, so for each one of these edges, if you think that this is, let's say, qubit I, qubit J, this means that I will have the term xij plus yi, yj, and then this is for each one of the edges of your graph. All right. I'm sorry, I can't really get a report from you guys. So if you have any questions during the talk, please feel free to interrupt me and ask me something. I mean, I suppose this is sort of familiar to you guys, but if it's not, then feel free to ask me a question. Okay. All right. So typically, if you have then, let's say here you have 6 vertices in your graph. Okay, now each one of these matrices is going to be, you can think of it as identity, tensor, and then X in position I, and then identity, blah, blah, blah. So each one of these is a 2 by 2 matrix. So this is in fact a 2 to the 6 by 2 to the 6 matrix if your graph has 6 vertices. Okay, so it's a big matrix. Okay. Now, fortunately, with this choice of interacting terms for each one of the edges of the graph, this matrix actually decomposes into very nice invariant subspaces. Okay, and invariant subspaces here will be the k excitation subspaces, and by that I mean the subspaces spanned by vectors that look like this. So say if again I have 6 qubits, if I have 6 qubits and k is equal to 1, then this is the subspace spanned by 1, 0, 0, 0, 0, and then 0, 1, 0, 0, 0, 0, and then 0, 0, 1, 0, 0, 0, and so forth. All right. So it's a 6-dimensional subspace if k is equal to 6, and if k is equal to something else, then it's a n choose k-dimensional subspace. All right. This is, of course, understanding that this is state ket 1 at qubit in position 1 and state ket 0s in the other qubits. Okay. So when I say that the k excitation subspaces are H invariant, it means that when H acts on this vector, the results are confined to the subspace spanned by these vectors. And of course, if I change only one guy or two guys, then I have the two excitation subspace and the same result holds. So this is a fancy way of saying that H is going to be a block matrix. Okay, so again, H here was a 2 to the 6 by 2 to the 6, so a 64 by 64 matrix, but it actually is going to have a bunch of blocks. First block is 1 by 1, and then a 6 by 6 block, and then a 6 choose 2 by 6 choose 2 block, and then so forth. Okay. So this sort of like helps a lot when you're trying to understand the dynamics of a system, because now instead of concerning with a big matrix, you can simply look to a small matrix. And the nice thing is with that choice of Hamiltonian, the one block that corresponds to the one excitation subspace, which is a 6 by 6 block, is actually the adjacency matrix of the graph. So hopefully most of you will be familiar with the combinatorics of graph theory. The adjacency matrix of a graph is a matrix with rows and columns which are indexed by the vertices of your graph, and then you're going to put a 1 if and only if you have an edge and a 0 otherwise. So exactly as you see there in the picture with the yellow shade representing exactly what's going on. Okay, so this is going to be a symmetric matrix, a 0 diagonal, and it basically encodes everything you'd like to know about the graph. And the fact that this matrix actually appears as a block of your Hamiltonian means that this can be used to fully describe the dynamics of the quantum walk if you start in a one-excited state for your graph, which is cat 1 here, cat 0 elsewhere. Exactly what is this representing when I put a dark shade at that vertex and a light shade in the other ones. Okay. And then this is the vector that represents this particular state in this one excitation subspace, which is 6-dimensional. And then after time t passes, this is going to be the vector that represents the state of the system. So this is the exponential of ITA times this vector. And then, of course, I mean, if you're familiar with Schrödinger's equation, you are fine with what's going on here because you understand exactly where this is coming from. And if this is the first time you see the exponential of a matrix, I understand that this could be a bit scary, but it's nothing but the solution of a differential equation. Okay, and this, you should understand this exactly as the only way you have to understand this, the exponential of a matrix, is in terms of its power series. Okay, which is exactly what you see there at the top of the page. So the exponential of ITH, simply imagine that this is a real variable and think of the power of the Taylor series of the function exponential of x. Now instead of x you have it and then a matrix. So basically you have a power series, and this is a matrix raised to the power k. Now, but fortunately, this doesn't really, I mean, this converges, let's put it like that, because this matrix has a minimal polynomial, and you can simply take larger powers and write them in terms of the smaller ones. So in fact, you're basically thinking of power series in I and t, and then you're good to go. Even better, you can write your adjacency matrix in terms of its spectral decomposition, which is you have an eigenvalue, its corresponding eigenprojector, okay? And you simply write your adjacency matrix of your graph as an eigenvalue times the projector. And then if you do this, it's straightforward to realize by using the spectral theorem that the exponential of ITH is simply going to be the exponential of the eigenvalues times I and t multiplied by the projections. Okay. And this is a very nice, easy to deal with matrix because you have a finite sum corresponding each one of the terms to a distinct eigenvalue of your graph. You have complex numbers, each one corresponding to the parameter t, which is the time, okay, of the system evolving, complex unity, and an eigenvalue. And you have a projection onto an eigenspace, which is a real matrix that you can very easily compute. Okay. And this completely describes a continuous time quantum walk on a graph, according to the model of that particular choice of Hamiltonian. But there are different choices of Hamiltonians, but all of the standard choices will correspond to a sort of combinatorial interpretation such as this, perhaps instead of the adjacent matrix or Laplacian matrix of the graph or some other matrix. Okay. Now, the nice thing about this equation is that it basically says that the quantum walk of a graph is completely determined by what happens when you raise a bunch of it times eigenvalues, and this is a sort of number theory, because if your eigenvalues are all, let's say, integers, whenever t is a multiple of pi, this is going to be plus and minus 1 for all of them. But if your eigenvalues are not integers, if your eigenvalues are irrational, which is the topic of this talk, then these things might not align nicely. Okay, and this leads to a sort of, well, not chaotic, but almost periodic behavior. And this, of course, these ERs will tell you that the eigenvectors, which you use to build these projections onto the eigenspaces, will also play a role, an important role. Okay. So one of the main problems people have worked on in the past 15 years or so in this model of quantum walks is the problem of perfect state transfer, which is you start your system with cat 1 here and cat 0 everywhere else, and you like that after some time t, you do observe cat 1 at a different vertex, okay, and cat 0 everywhere else, right? And this would be quite nice if you think that your graph is actually modeling a device that could be used to transfer states. Okay, and this basically means that if this is the initial state of the graph, you'd like to find a time t that allows you to multiply and a particular choice of adjacent matrix of a particular graph. You'd like to find t in a particular graph, and then when you multiply this matrix by this vector, this is actually what you get, right? Perhaps multiplied by a global phase here, but this doesn't really matter, and we don't really need to worry about this at all. Okay. And this is exactly the definition of perfect state transfer at a particular time. Okay. Now, it's very easy with this formalization that I'm presenting to you to actually identify necessary and sufficient conditions for a perfect state transfer to hold. You can simply use the spectral decomposition of this matrix. So I am writing this matrix. So this matrix that you see here is exactly what you see here. Okay. And then you can simply picture that here actually you do have, excuse me for a second, here actually you can picture that you have the identity matrix times this. And now the identity matrix is exactly the sum of the projections onto the eigenspaces, because this is in fact a full diagonalization of the space. Okay, the matrix A is symmetric, so we get a full diagonalization in terms of orthogonal eigenspaces. So if you sum the projections onto orthogonal eigenspaces, you actually get the identity matrix. It's all standard linear algebra. And then, and now what you could do is simply multiply both sides of this equation by each one of these projections. So the nice thing when you multiply orthogonal projections by each other is that they cancel each other out. And if you multiply a particular orthogonal projection by itself, it's an idempotent, you get the same thing. So if you multiply both sides of this equation, all terms of the sum will disappear except for one particular. And then, of course, because these guys form a basis, this equation in the middle is equivalent to enforcing that for all of these projections, you have the equality without the sum. Okay. And this basically is now equivalent to two particular conditions. Well, the first one is to realize that this is a real vector. This is a real vector. So it must be that this term here is plus or minus 1. And it must be that this vector is plus or minus this one. Okay, so you cannot have something like this vector being not parallel to this one because you're just multiplying it by a number. All right, so these are parallel vectors. It could be both 0, of course. And then in which case this guy is free to be whatever he wants to be, and then these eigenvalues will not really play a role in the quantum walk in the particular verses. All right, but for those which are not 0, then you have exactly this necessary and sufficient conditions. For all R, you must have that these vectors are parallel, plus or minus each other, and that this e to the I t theta r is plus or minus 1. Okay. And this is exactly what I mean when I say that you have a sort of geometric condition, which depends on the eigenvectors of your graph, and you have a number theoretic condition, which depends on the eigenvalues. Now let me move forward and say that this is a problem completely solved, completely well understood. You can generate several examples. There are thousands of papers showing phenomena of perfect state transfer in different classes of graphs. There is a polynomial time algorithm that works in a classical computer, receives a graph, and determines whether or not for two verses of that graph there is perfect state transfer. So if your task is to build a quantum system with perfect state transfer, the only thing you need to do is follow a recipe. Okay. There's still a couple questions, a couple details we don't really understand, but I mean, in terms of global questions of generating examples of deciding whether or not a particular graph admits it, we're good to go. Okay, and then this condition has been defined as saying that the two verses 2 and 4 strongly co-spectral, and this has to do with counting walk symmetries, and it is a condition decided in polynomial time, even in exact arithmetics. And this condition has to do with the eigenvalues satisfying certain parity things. So for example, if the eigenvalues are all, let's say, multiples of 4, you cannot really pick your t to be pi on 4, for example, because then all eigenvalues are going to be -1. But you actually want to enforce that this is going to be plus or minus 1 exactly when this is plus or minus 1. Okay. This condition here basically implies that the eigenvalues have to be quadratic integers. This is a result due to Chris Godsil in 2012 or something. It means that they have to be written in this particular fashion. And then once you understand this, it's not easy, it's not difficult actually, to decide whether or not there is a time t that will solve these equations plus or minus 1 for each particular choice you want. Okay. Now, the topic of this talk, the main topic of this talk is very good state transfer, which is, well, a perfect state transfer. Yes?
Can I ask a question?
Of course, please.
Yeah, so in the derivation of the vector to be plus or minus 1, you rely on the projector to be all real number?
Yes.
So is that always the case?
Yes. Yes, that's a very good question. So in this particular model, we are assuming that our graphs are undirected. So the adjacency matrix is going to be real symmetric, and therefore the eigenvectors are going to be real vectors. So all the projections are going to be real matrices. Okay?
Okay, I see. Thank you.
Yeah, sure. Of course, there is a nice theory if you allow for directions in your graph, and this was actually the topic of Rodrigo's talk a couple weeks or a couple months ago. So if you put a direction here, you can encode this direction in your matrix, still leaving the matrix, still maintaining the fact that the matrix is Hermitian by putting here I and then minus I here, for example. So this is a way of encoding direction, because then you have a sort of asymmetry where the minus sign goes, and then this basically determines where the arrow points to. So of course, if you do that, then your eigenvectors are no longer going to be real, and then the same analysis doesn't hold. You have to be more careful, okay? But for this particular model, I'm simply assuming undirected graph, so everything is real. So this is the main problem we are concerned now, which is, well, suppose a perfect state transfer is difficult to find. Most graphs do not admit it. And So for example, a very natural candidate to admit perfect state transfer is simply the path, unweighted path. Well, it doesn't unless you only have 2 or 3 vertices. However, this would be a very, very nice quantum network for you to transfer your states, right? Because it would be arguably the cheapest thing you could ever build. Now, so this motivates the question, well, if instead of perfect, what if I am satisfied with only approximation? So this here is meaning that this occurs, this sort of like approximate equality occurs precisely if for each epsilon that I want to be far from this guy, I can find a t that puts this vector within that ball of radius epsilon around this guy. So if you pick small and smaller values of epsilon, you can find larger and larger values of t that will put this thing on the left on the ball of radius epsilon around that guy. Okay. And then again, we can show that this condition is, so this is all known results. We can show that this condition is equivalent again to necessarily having that this projections are going to be plus or minus each other. It cannot be different than this, otherwise you cannot get as close as you want. There's going to be always a limit to how close you want to get, but you want to get arbitrarily close, so they have to be plus or minus each other. And then the approximation is going to happen here. So the e to the it theta r is going to be plus or minus 1, except that approximately. So you want to find larger and larger values of t that will make these guys closer and closer to plus or minus 1, right? And this exactly means that if you have a sequence of your eigenvalues and a sequence of values 0 and pi, which are exactly going to be, so you want this to be, you want t theta r to be 0 when this, let me put it like that, you want t theta r to approach 0 when you want e to the I t theta r to approach 1. And then, of course, you want this to approach pi when you want this to approach minus 1. All right? So basically, you're asking whether or not for a given sequence of eigenvalues and a given sequence, prescribed sequence of 0 pi, 0 pi, 0 pi, whatever, however this plus and minus alternate here, you can find larger values of your times t such that whenever you multiply your time t by this thing, you approach this sequence. So this is a standard question in dynamical systems in the 1800s. And it's been, I mean, this appears not a place in physics. And there is a nice answer to this question. So again,
sorry.
Yeah.
So why you need the time to be large? So if you need the value to be 1, your t times 0, t can there be 2 pi, multiple of 2 pi?
Sure. What I mean is this is mod pi, mod 2 pi, sorry. That's what I mean. This is all mod 2 pi. Should have probably written that here. This is all mod 2 pi. Okay.
Then why the necessary of t to be large?
Because basically, well, if you sort of like plot this, let's say if you plot the absolute value of the difference of these two things, something like that, you will see that this will sort of like look like this. Okay. Let's say approximately. I mean, it won't look this nicely. It will be something that kind of goes up and then down and then up and then down and then up and then down. And then of course here is one, something like this. And then you want to get as close as possible to this guy. Now, when you're moving, your time moves up, you hit something here, but then you want to get closer. So you sort of like need to move forward a little bit and find the next time that this gets better. So if you get this, if you get the epsilon that you want to get as close as epsilon to this thing, then you sort of need to search for a larger time until you get there. So there is no convergency here in the sense that this is not something that will get closer and closer and closer and closer like a logarithm or something like that. You see?
So it's not possible to be periodic?
It is possible to be periodic. So this is, if it is periodic and if it touches 1, then we are exactly on the perfect state transfer case, which is what came before. And if it is periodic and never surpasses a particular thing here, then you do not get pretty good state transfer. So pretty good state transfer actually does happen when it's not periodic. And then when you can get as close as possible, as close as you want. To get as close as you want, you cannot be reproducing past behavior, right? Otherwise, you're not improving. You see what I mean?
Okay, I see. Thank you.
So this is the main question, whether or not when you can find values of real numbers that when you multiply the sequence of eigenvalues, you get as close as you want to 0 or pi modulo pi. Okay. Now, there is an answer to this. It dates back to the 19th century. It's a characterization given by Kronecker, which says that this phenomenon occurs. You can find larger and larger values of t, so that this approaches this, whichever prescribed sequence you have there. If and only if for all integers that you can find which satisfy this equation, meaning a integer combination of your eigenvalues equal to 0, it must be that these integers also satisfy this equation. And this equation is for all the tn that when you multiply, you want to get to pi. So for all the indices that you want to get to pi, the indices of the integers corresponding to those guys, when you sum them, they have to be even. Okay, now this is a theorem due to Kronecker. It's a very nice theorem. It's not that difficult to prove. It's sort of like a 2 or 3 page long proof. It's not something you would come up on your own if you tried right now, but it's not something you would, I don't know, be extremely difficult to prove. Okay, and it's a very nice result. But unfortunately, it's not algorithmic, the proof. It's not constructive. It doesn't tell you exactly how to test this, because there is a for all here, and the theorem does not give you a way of describing which are all the integers that satisfy this, let alone give you an expression for the integers for you to check whether or not this is true. So this is the main work that we did. Okay, our work consisted in transforming this into something you can actually check algorithmically. And therefore, if you're given a graph, you can actually decide whether or not pretty good state transfer occurs without having to require to numerical simulations or things like that, because those are unreliable in the sense that you do not want to be simply performing a search here for large values of t, because it could be that you're simply in bad luck. And eventually, pretty good state transfer could kick in, but only for very large values, and you wouldn't get there. Now we have a way of actually checking whether or not this condition is satisfied. Okay. So how does this work? So the eigenvalues of A are typically roots of polynomial of large degree. So they are algebraic integers, but not things that you can typically write as sums of square roots or things like that, because, well, if the degree of these things are larger than 4, then you're doomed. So says Galois. And then basically you have to have a way of dealing with irrational numbers, which does not require you writing them as, well, expressions that involve square roots. So how do you do that? And the answer lies in standard algebraic number theory. So if you have a polynomial p, and in my mind now this is going to be the characteristic polynomial of the graph whose roots are the eigenvalues, you can simply think of the field, the extension field that starts with irrational numbers and adds these guys. So this is basically the set of all things that are rational numbers times powers of these things, powers of this eigenvalues. Okay. So this is a field. It lies between Q and R. It's an extension field of Q, and it receives the name of a splitting field of your polynomial. And if you ever took a Galois theory course, this is probably the, I don't know, a third or fifth lecture. So it's a simple result. It says that for all things that look like this, you can always find a real number that actually generates this whole thing. So each one of these guys are going to be polynomials in this particular real number. Okay, and this particular real number is an algebraic number. It admits a polynomial of smallest degree, which maps this number to 0. Let me give you one example. If you've never seen this before, I know this is all starting to sound a little bit too abstract, but it's actually quite concrete. So this is the standard example you will see in your Galois theory course. The rationals extended by square root of 2 and square root of 3. So this is basically all things that you can write, which are rationals times either this guy or both, or combinations of them. Okay, now things that look like this. It is actually true that this thing is equal to this thing in the sense that there is a way to write square root of 2 as something that looks like this. And there is also a way of writing square root of 3 as something that looks like this. And therefore you can write everything that is in here as something that looks like this. This is actually, you will need powers up to 4 to accomplish this task, but you will succeed. Okay, so this is the standard example. It shows you that this is a primitive element to the extension field generated by these guys. Now, the elements of this extension field are polynomials in alpha. And it's true that whenever you have a polynomial in alpha equal to 0, it means that the minimal polynomial of alpha actually divides that thing. This is all standard algebraic number theory. And for each one of these guys, eigenvalues of your graph, it means that there is a polynomial with integer coefficients so that there is an alpha, and this polynomial with integer coefficients apply that the real number alpha is actually equal to each one of these eigenvalues. And this is arguably the best way one will ever have to represent algebraic numbers. Okay, so this is a root of a polynomial of, I don't know, degree 10, but you can actually represent it by a polynomial with integer coefficients. So a string of integers actually represent your algebraic numbers. Very nice way. Okay. And then this question now becomes simply a question of substituting each one of those guys by the polynomial. And then, so you want to know when this is true. Now you substitute those eigenvalues by the polynomial in alpha that gives each one of them. The degree of this thing is less than the degree of the minimal polynomial of alpha. So this equality actually implies that each one of the coefficients have to be 0. So this is in fact a system of equations with integer coefficients, and you're trying to find integer solutions. Okay? Each equation corresponding to a particular degree of alpha. You want all coefficients of this polynomial to be 0. Okay? And all these coefficients are integers, and these are integral variables. So you're trying to solve a Diophantine linear system, which is basically something that will, yes?
So can you remind me why you need the integer coefficient?
Because this is what comes actually from Kroneker's theorem. So Kroneker's theorem tells you that the condition that I'm testing for pretty good state transfer is equivalent to checking that for all integers that satisfy this, they also satisfy this. So what I'm trying to do now is find a way of finding all of these integers. Okay.
Find all possible solutions.
All possible solutions, yes. Because I need to, ideally, and this is actually what we achieved, you can parameterize this, have all possible solutions, and then write this in terms of free variables, and then check whether or not it's going to be even for all free variables. Okay.
Okay, thank you.
Yeah. So this is the gist of it. You have a big matrix of integer things. You want to find integer solutions that will be 0 to each one of the equations. Okay. And the standard ways, fortunately, this is well understood. The standard way of solving a Diophantine linear system is to write a standard form for the matrix. You can do with the Smith normal form. Hermite normal form also works. It basically means that for each matrix which is integral, you can find integral matrices with inverses which are also integral matrices, so that this product is a diagonal of integers. This is possible. This is sort of like a linear algebra magic. So it basically means if you have this sort of diagonalization of an integer matrix by integer matrices with integer inverses, you can now simply solve this with integer variables. And you can basically see what's going on there. I think I'll have to speed up a little bit, otherwise I won't go through all my slides. So I'll leave the details for you guys to work that out, but this is all explaining details in our paper, okay? And it basically means that you can find a full parameterization of the integers that satisfy all the equations. So this is an integer matrix, and these are free integral variables. So it means that you can decide whether or not this sum is going to be even by simply enforcing that all of these coefficients that will appear here will have to be even. Because of course, if a free integral variable appears with an odd coefficient, you can simply zero everything else and put that variable an odd number. So it's simply a matter of checking whether or not all the coefficients will be even, and we are done. Okay, so this is the result that my master student Pedro and I worked on and his project. Okay, and basically we achieved this characterization. I mean, unfortunately this doesn't lead to a very efficient algorithm, because it relies on you being able to compute these polynomials. And these polynomials, even though you have efficient algorithms to compute the polynomials can be very large. So those algorithms, they depend on the size of the polynomial, and these polynomials could be as big as n factorial. So underlying this whole process, there is an exponential time algorithm, unfortunately. And I don't think we can surpass this difficulty. But for many small graphs, I mean, we tested a bunch of graphs up to 40, 50 verses. We could actually check and find new examples of pretty good state transfer, okay, using this algorithm. Now, let me move forward a little bit to say why our paper actually has 12 more pages after this, because we're able to find nice applications of this technology to study other things related to quantum walks. So what's going on here is this. You're writing the quantum walk matrix of the graph C5. So let me just put here. So C5 is this graph. So the hypothesis here is that you have 5 qubits. They interact with each other in a cyclic fashion. And you write your quantum walk matrix, which is going to be a 5x5 matrix parameterized by this parameter T. And then we are plotting here what you would see in the complex plane if you plotted the 1 entry of this matrix as T moves forward in time. So it starts with T equals 0, and that entry is equal to 1. And then as T grows, we sort of observe a curve that sort of like moves around in the complex plane, sort of like drawing this thing that you guys are seeing there. Okay, so it's a sort of, so what you're seeing here is the image of this thing as T belongs, let's say, to the interval 0, 100 or something like that. Okay. And in 2019, I was at this conference and I was basically talking about quantum walks, and I showed this picture, and I mentioned that I had no idea how to understand what was going on. Why, for example, there is a fivefold symmetry in the picture here. I mean, is this anyhow connected to the fact that this graph has a fivefold automorphism? This physicist, Reinhard Werner, was sitting there in the audience, and he had a bunch of nice things to discuss about this. And we kept in touch and kept collaborating. And then recently I realized that all the technology we had before to solve pretty good state transfer could be very nicely applied to understand exactly what's going on here. Okay, so basically, you can write this particular entry of the matrix as this. There are 3 distinct eigenvalues in this graph. This number is 1/5, 2/5, 2/5 are coming from the eigenvectors, okay? And then you have the 3 eigenvalues, theta 0, theta 1, theta 2. And now we know how to describe all linear dependencies, all integer dependencies of these things. In fact, for this particular example, theta 1 and theta 2 are free, independent, rational numbers, but theta 0 can be written as -2 times theta 1 plus theta 2. And by recovering these expressions that relate one eigenvalue in terms of the others, we can actually very nicely describe these things. So, for example, and we would like to answer the questions such as, why do we have rotational symmetry, and which are these curves that you can see here, sort of like bordering these shaded regions, for example. And then here basically comes the technology that allows us to perform this analysis, which is you have a parameter t, and you're multiplying t, as t is going to be a free variable, by a vector of 3 eigenvalues. And then, of course, this must be understood as something mod 2 pi, because whenever t times theta 1 goes above 2 pi, you restart, right? So this is indeed a torus, a 3-dimensional torus. And then you're basically a curve in your torus. You start with t, you multiply t by these 3 numbers, and then you're mapping these to a torus, and then you have a curve in the torus, and then by means of this function, you're mapping this curve in the torus to the plane. It's a sort of like you start with a real number in an interval, you go to the torus, you have a curve, and then you sort of like squish this curve onto the complex plane. Okay? So you can simply understand that you have 3 variables in your torus, but you know that one of them is determined by the other. So it means that actually you have a subspace of your torus, a 2-dimensional subspace. You have 2 free variables, but the third is determined. And basically what the theory, Kroneker's theorem and Weyl's theorem will tell you is that this curve will be dense in this subspace, the subspace with these 2 free variables which the third satisfies this. So in fact, this curve here will sort of like fill a sort of like a ribbon in your torus densely and uniformly. So it is a region of your torus. Okay. So you have these 2.
Sorry,
Yes.
can you explain and why it is dense?
Oh, this is a theorem. Well, Kroneker's theorem will guarantee that it's dense, because it basically, let me go back here and just simply give you a quick reason. If by any chance your eigenvalues theta 0, theta 1 up to theta d were independent from each other, meaning that there is no way you could write any one of them as an integer combination in terms of the others, it means that there are no integers satisfying this, and therefore this condition is vacuously true. And therefore you could approximate basically, I'm writing here one specific version of the theorem, but basically then you could replace the 0 pi by anything, and it means that you could approximate anything you wanted. So I'm sort of skipping this detail because then you would need to go through Kroneker's theorem in its full form to understand what's going on. But it's a consequence of the fact that in the rationally independent eigenvalues, Kroneker's theorem guaranteed that it's going to be dense. And then Weil came in the 20th century and actually told us that it's going to be uniform, in the sense that the amount of time you will spend in each little square in the torus is actually the same for each square. So it's not more dense here than here, it's uniformly dense everywhere. Okay.
I see. Thank you.
Sure. And then you have this this map, which describes the global geometry of the region. And actually here in this slide, what you can see is the curve, the 1-1 entry, which is exactly this one here. And if actually, so this is the curve that you're seeing in this first picture. And if you plotted an off-diagonal entry, it actually would look like this. So the expression is not this one anymore, it's something different, but you could plot that curve and get some curves for this particular example, the cycle C5. If you simply now replace each one t theta 1 by z1, a free variable in the torus, t theta 2 by z2, a free variable in the torus, and t theta 0 by minus 2 times z1 plus z2, because theta 0 is minus 2 times theta 1 plus theta 2. So these are free variables in the torus. Now you should expect that instead of describing a curve in the torus, this is now describing a region. And these things that you see here are plots of the grid in this region. So simply imagine that you have your torus, right? And then you have a region of the torus, and then I have a sort of grid, like a square grid, and I'm plotting this grid here. And then this sort of like shows you that you have a complete correspondence between these two things, and this correspondence actually has to do with the density, right? So the grid is being mapped to the plane as dense as the curve seems to be. And this is sort of like is an example of why Weil's theorem is correct. That this thing is a dense thing. It's quite nice. And then by looking at this, we felt that we now had a complete understanding of not a complete, but a very nice way of understanding the geometry of this. So we're able to prove a result such as for CP cycles with a prime number of vertices, we could prove that you do have a pth rotational symmetry. Actually, we could show that for any graph, you would find n rotational symmetry if and only if certain sums of coefficients expressing eigenvalues would be congruent to 1 mod n. Won't really have time to go into the details, but you can check in the paper. So this technology allowed us to understand why this has a 5 rotational symmetry, and it has nothing to do with the fact that there is an automorphism here of order 5. So it's a very funny situation where these two things look like they should be related, but they're not. It's a coincidence. And I can find graphs which have automorphisms of order 5, and the pictures will not look like this at all. We're also able to completely describe these curves that you see here in the border. These are simply the singularities of this map. So basically, if you compute the partial derivatives and you ask that these derivatives to be parallel, you'll get two solutions, and each one of these solutions will describe each one of these curves. And we saw that for odd prime cycles, we could get a full description of these curves, but for autographs, it's not very easy in general, because this is not something you can solve exactly for in general. I mean, you could for this particular example, but in general, it's difficult. It would be very nice to have a nice way of solving this, but standard simple methods cannot. But for graphs which are cycles with prime number verses, we could do that. And we also did in this paper more examples of geometric properties that we could derive because we're able to compute those polynomials that tell you exactly how the eigenvalues relate to each other. We also came up with an attempt on how to find the supremum of this maximum probabilities of transfer. We completely solved the decision of whether or not this supremum is equal to 1. And we came up with a way of attacking the problem of actually computing this supremum when it's not equal to 1, but we didn't really succeed to finish this task. So we actually left that as an open thing, but the main open problem of our work is how to find times t for which PGST occurs. We are able to decide whether or not it occurs, but we do not know how to compute the times that will give you the good approximations. And I truly believe that this should be a important problem, because this is the one thing that is left to make PGST a useful quantum walk phenomenon. Okay, and that's it. Thank you very much.
Thank you. Is there any questions from the audience? Okay.
Sorry, maybe I ask a question.
Yes.
And when I see in your paper, you will expand the expansion ITA, the evolution to some power, and you did not discuss in the talk. So in which case you need to discuss the behavior of this exponent IT.
I'm sorry, I think I did not understand the question. There was an echo, and I think I missed one of the keywords in your phrasing. Could you repeat the question, please?
I think the starting point of your work is discussing the evolution of the Hamiltonian evolution.
Yes.
And in your talk, it seems the discussion of this polynomial of the expansion of this Hamiltonian simulation seems not important. So is there anything I missed out? I mean, you don't really need the expansion of the Hamiltonian simulation for your derivation.
You're saying that I do not need the expansion of which matrix? Can you tell me basically the slide of which one of what your question refers to? I'm sorry. Is it?
I'm asking you, in your talk today, you are expanding your behavior all in the projector. But
Yes.
In your paper, I just look at it looks like you also discuss the Hamiltonian simulation expansion ITA
Sorry.
directly, so there is no need to expand them into some eigen projector. Is that true?
Okay, I'm not sure if I got exactly what you mean. You said some matrix, but let me put it like that. It's definitely necessary when you're studying quantum walks to in a graph to analyze each one of these E sub r independently, because they are all orthogonal to each other. Okay, so whatever happens here for one particular r will not be affected by any other one. So if you want an equality such as this to occur, you do need to look at each one of those. Did that help you answering your question?
Yeah, I think, yeah, I know. So you need to decompose them into independent part and do the discussion.
Yes,
Yeah.
yes,
Okay. Thank you.
definitely, yes. Yes. So down here, when I was discussing these geometric properties, there's each one of those eigenprojectors are basically determining these coefficients, and they play a very important role in the sense that we were able to, for example, solve this problem here because these coefficients are nice. Now, if you look, for example, for the off-diagonal entries, and you ask which are these curves here, you would run into trouble because these coefficients will not be so nice. And these coefficients are coming from the eigenprojectors. Okay.
And yeah, and so one more question. You said the C5 symmetry, it seems a coincidence for this graph, but it is also determined by the eigenvectors. So I think probably it's not a totally coincident. It just need to check the eigenvector, which may be determined by this
Okay.
shape.
Yeah. Of course. I mean, this graph determines everything, so it cannot be a complete coincidence. But let me put it like that: the Peterson graph, right? Not sure if you're familiar with, but the you have the start with the C5, okay, and then you put this thing here. So, I mean, this has a fivefold symmetry. You would, in principle, expect that if the connection has to do with the symmetry of the graph, then whenever you plotted this in the complex plane, it would need to look like a star or something like that, but it actually doesn't. It actually has no symmetry except for the reflection above the real axis. It's a curve that looks something like this and nothing else. So it has more to do with the fact that the eigenvalues here are quadratic integers, and that you can write one eigenvalue in terms of the orders with this particular coefficient, than with the fact that these are fives. Okay? The fact that we observe this fivefold symmetry.
Yeah, okay, I see. Thank you.
Yeah.
So, Gabriel, I have a question. Does the Kramer lemma use a lot in this field?
Kronecker lemma, you said? If it's used?
Kronecker lemma.
Yes.
Yeah, I think the main lemma you used in this work.
Yes.
Yeah.
It is. It is. This one you mean, right?
Oh, yeah. Does this lemma used a lot in the related work?
So this is an if and only if, okay? And I've seen uses of this thing dating back to some 15 years ago, which only use one direction. So instead of looking at a characterization, people simply basically, if the eigenvalues were independent from each other, there would be no integer satisfying this. This would always be satisfied, and then you would always have PGST. So this has been used many times before. Now, the first time that I actually came across this result used here was in a paper by Luc Vinet and Alexei Zhedanov. They were discussing PGST in paths, and it was the first time actually I realized that there was an if and only if condition, and the if and only if condition allowed for the situation where the eigenvalues were not necessarily independent, but you would need to study the dependencies. And then the first time I actually used this, I myself was in a paper in 2017 to characterize pretty good state transferring paths according to the Laplacian matrix model. I've seen some people using it later, but it's actually less common than it should be. Because if you want to study pretty good state transfer in any graphs, you should be using the full force of this thing.
Okay, I see. Thank you.
Sure.
Is there any further questions? Okay. So if there's no further question, that thanks Gabriel again.
Thank you. Thank you very much. And if any one of you guys is particularly interested in these questions that I left here in the end, then please send me an email. I'll be happy to discuss them further.
Yeah.
Okay, thank you.
Thank you.
Okay, thank you, Gabriel. Very nice to see you. Sorry I'm late.
Not a problem, not a problem. But thank you for the invitation anyway. Thank you.
Yeah. So my name is Ming-Shu Xie. I'm the leader of the group, and indeed we are very interested in the quantum work-related algorithms. So that's why we we constantly go back to your group for some interesting results.
I'm very happy to get in touch with you guys. I'll be very happy to discuss any of these topics further. I mean, we can keep debating over email or schedule these meetings with these weird hours either for myself or you guys, but I'll be happy to keep debating, yes.
Yes, sure. We do have some ideas of your previous results, and maybe we would set up another discussion a little bit later with you.
Fantastic. I'll be happy to. Yes. Thank you.
Okay, great. Thank you for the talk.
Okay. Thank you. And you guys have a good day. Bye-bye.
You too. Bye.